Okay, so we're going to graph this exponential function. This is an important function in statistics, although that's not going to be super relevant for what we're doing, just as sort of a fact. We are going to start, as we always do, by thinking about what the domain is. So the domain is all real numbers, right? Because we can take any value we want, square it, and raise it e to that power. So the domain is all real numbers. Okay, so now we have to consider first derivative test. So we take the derivative. Now this requires chain rule, right? So derivative of e to the negative x squared is e to the negative x squared times the derivative of negative x squared, so negative 2x. That's chain rule, which I can write as negative 2x divided by e to the x squared, right? So my negative exponent, my hint always is to try to write that as a fraction. So we write that in the denominator. So we want to know where is f prime either 0 or undefined. This thing, f prime will be 0 when the numerator is equal to 0. So that's going to happen when x is equal to 0. And the derivative will be undefined, actually never, because we're looking for wherever e to the x squared is equal to 0, but that never happens. So we only have one critical point showing up here. So we consider our number line, and we think of values of the derivative less than 0 and then greater than 0. If you pick a value less than 0, it turns out you will get a positive first derivative, and so that's telling you that the f is increasing on that interval. And then it'll be negative after 0, so f will be decreasing after that. So we have something going from increasing to decreasing, so that tells us that we have a local maximum occurring at 0 comma something, and the something is f of 0, which is e to the 0 or 1. So local max at 0, 1. Okay, the concavity test, we do everything again for the second derivative. So you can do this as either a product rule or a quotient rule. I think I might as well just stick with quotient rule since we have a quotient, and we want ultimately our answer to be a quotient. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. Again, that's a little chain rule. All over the denominator squared. So that's negative 2 e to the x squared. This negative and this negative make it plus. And then we've got a 2 times 2 is 4x squared e to the x squared. And this is all over e to the x squared quantity squared. So I can factor e to the x squared out of the entire numerator, or one way of thinking about it is I'm really just going to be canceling it out of the numerator and the denominator. So I'm left with negative 2 plus 4x squared all over 1 copy of e to the x squared. Now we want to know, remember this whole thing is the second derivative, we want to know where is the second derivative either 0 or undefined. So this will be, the second derivative will be 0 whenever the numerator is equal to 0. So that's solving x squared equals 2. So x, wait, did I do that right? No, I did that wrong. Let's see. Dividing by 4. Okay, that'll be 1/2. Sorry, let me erase. Right, divide both sides by 4, we get a half here, right? So x will be plus or minus the square root of a half. That doesn't look like a 1, sorry. And then the denominator 0 is actually never, so we're not getting any values there. So we're really just looking at what's happening on the interval between negative the square root of a half and then positive the square root of a half. So it breaks it up into 3 intervals. If we look at the second derivative on these intervals, we get a positive result, then a negative result, and then a positive result. So that's telling me that f is going from concave up to concave down, back up to concave up. So we get inflection points at negative the square root of a half, comma something, and positive square root of a half, comma something. To get those somethings, we go back to the original. So in both cases, that's going to give us e to the half, or the square root of e, whichever way you like writing it. So those are our inflection points. There's our local max. Let's sketch it. So we got a local max at 0, comma 1. And then at positive square root of a half, comma square root of e, we have an inflection point. And then symmetrically over here, inflection point. Okay, so what's happening? We are increasing all the way to 0, and we're increasing in a concave up fashion until we get to the first inflection point. So increasing concave up, and then we are increasing concave down, right? Because we're still concave down. We're going to stay concave down, but now we switch to decreasing. And now after the square root of a half, we stay concave up, still decreasing. And what you'll see is we get the bell curve, which is why I talked about this being important statistics. So a couple of little side notes here that how did I know that these didn't cross the x-axis down here? Well, technically I really should look at the end behavior here. So as x goes to infinity of our original function, which I can think of as 1 over e to the x squared, we see that the denominator grows very large, and so this thing goes to 0. So that tells us our end behavior here. And likewise, if this were going to negative infinity, this still would only be approaching 0. So those are our horizontal asymptotes. So in this problem, unlike the polynomial ones or some of the other ones, we didn't really need to know the end behavior. Here, it was helpful to see it. Also, if you had tried to find any x-intercepts here, we would have found no real solution. So that also would have told us that we knew that the graph wasn't touching the x-axis. Okay, so there's that example.